Is the recording started?
Yes, recording started.
All right. So, hi everyone. We are Group 39, and our project is Comparative Study of Machine Learning and Deep Learning Models. So, my name is Shabrin Alam, and I will be starting with a presentation with my team member, Shariar and Omar. So, together we will go through our work on this project. So at first, we would like to showcase our respect to the Larkia people and the First Nation custodian, the land where we study. We pay our respect unto elders past and present and to all the First Nation people. So in the background, machine learning and deep learning are widely used today to solve real world problems. On one side, we have machine learning algorithms like decision tree, random forest, and naive Bayes, which are simple, interactive, and fast. On the other side, we have deep learning models such as artificial neural networks, which can capture very complex patterns. The key question is which one is the better for the real data set like this. So by comparing ML and DL, so we can understand not only which performs better, but also the trade-offs in terms of accuracy, efficiency, and interpretability. Moving on, the aim is first to build and implement several ML and DL models, including decision tree, forest, random forest, and naive Bayes, and secondly, to compare their performance using evaluation metrics like accuracy, precision, recall, F1 score, and ROC AUC. Thirdly, to identify which model performs best for the income prediction. And finally, to discuss the trade offs between accuracy and interpretability and speed. Moving on about the data description, for this study, we used the adult income data set from the UCI machine learning, and it has about 48,842 rows and 14 features, a mix of categorical and numerical attributes like age, work class, education, occupation, and hour per week. The target is whether someone earns less than 50K or above 50K per year. So we chose this dataset because it's large and realistic. It includes both categorical and numerical features, which make processing interesting, and it's a benchmark dataset often used in ML research, which means we can compare our results with our studies. Moving on, in the row, dataset missing value were marked with a question mark. We replaced those with none and dropped those rows, which still left us with a large dataset. And it's about 32,561 rows and 15 columns. We then did some processing, used one hot in encoding to convert variables into numeric, normalized numerical variables like age and hours per week, so they were on the same scale. Finally, split the dataset into 80% training and 20% testing. This prepared dataset was ready for analysis and modeling. And now I will like to hand over to my colleague, my team member Omar Farouk, who will talk about the EDA and the feature engineering.
Hello everyone. I will be talking about the exploratory data analysis, the feature engineering, and model training. So, firstly, to better understand the data, we carried out the exploratory data analysis. We started by looking at the class balance. About the 76% individuals earn less than 50K, and only 24% earn more than 50K. This imbalance is important because models may lean towards predicting the measured class. Next, we look at the distribution of the numerical features. For example, most of the people aged between 20 to 50 with a peak around 35 years old. Most people work 40 hours per week and with a clear spike at 40. For capital gain and loss, the majority of the values are zero and with only small group showing higher values. So we only analyze the categorical features much as the work class and the marital status, which showed strong links to income. So finally, we used correlation heat map. It actually shows the features like age, hours per week, and the capital gains had the strongest correlation with the income. Though the correlation were not very high, this means no single feature predicts income alone. Models need to lean from the combination of the features. Can we go to the slide 9, please? Thank you very much. And now I'm going to talk about the feature engineering. Once we understand the data, we prepared it all for the all models. Firstly, categorical features were not one hot encoding. Secondly, numerical features were normalized. Then the target variable was mapped into binary values with 0 for less than 50K and 1 for more than 50K. I'm sorry, 0 for less or equal than 50K. After completing the pre-processing and cleaning, our final dataset was 32,561 rows and 15 column or 15 features. We also ensured the train and test dataset is split into stratified to preserve class balance. This step was crucial to make sure all the models work efficiently on the data. Can we go to the slide 10, please? Thank you. The model training, now I'm going to talk about the model training and setup. For model development, we used Python and Jupyter Notebook, obviously, with the libraries such as Pandas, Scikit-learn, TensorFlow, Keras, Matplotlib to plot the diagrams, and then Seaborn. We trained the 4 models. Firstly, the decision tree. We tuned max depth, then the random forest with 100 trees, then the naive Bayes, which is Gauss naive Bayes using Gaussian naive Bayes, and then artificial neural network. It is actually the basic of the deep learning we used here with 3 hidden layers, the ReLU activation function, and the Adam optimizer. With each model was trained one on the training set and tested on the test set. We evaluated with the precision metrics like the accuracy, precision, recall, F1 score, and the ROC AUC. This is the metrics to measure the performance of the model. Then, so we could compare them according to their performance. So that was all for my part. So I'm going to hand over all these things to my next teammate, Shahriar. Shahriar, please carry on.
Thank you, everyone. This is Shaurya. I'll talk about the result and decision and finally the conclusion. So, for the first result, this slide shows that the random forest model was the best performance with the accuracy of 85.9% and the highest ROC and an AUC of 0.907. And then the ANN came close with an accuracy of 82.6% and the ROC of the 0.877. And then the decision tree performed the moderately at the 81.6% accuracy with the AUC of 0.75. And finally, the naive Bayes model performs the weakest with only the 52% accuracy, but it is the very high recall about the 95%. This means that the correctly identified most of the positives but misclassified many negatives, leading to poor precision. And the final, the ROC curve. Next slide. Thank you, Gabriel. The ROC curve confirms this, the random forest and the ANN clearly stored the outcome to compare to the others. And finally, the decision. So next slide, please. So for the decision, this result, we can draw the several insights. Random forest and ANN are the most effective models, balancing accuracy of and generalization. Decision tree is the interpreter, but not as accurate and tends to overfit. And naive Bayes was the faster, but the independence assumption doesn't fit this dataset, which hurt its performance. So our methodology is also impact one hot encoding and scaling are essential for naive Bayes and ANN. The state split ensured the fair and testing, and using ROC AUC gave us the threshold independence way to evaluate the models. So to conclusion, random forest was the strongest model overall, and with ANN was close behind. Decision tree is the interpreter but less accurate, and naive basis was quick but gave poor accuracy. So that's from our part. Thank you, everyone. Thank you for listening. We are happy to take our any question.